Our next topic in this chapter is described as solubility equilibria. Solubility equilibria are the problems that we worked earlier called Ksp, the solubility product constant for salts. It's asking us to question if it dissolves and how much of it, and if so, how much the Ksp, the solubility product, allows us to determine the amount of a salt that is dissolved per liter of water. This is known as solubility. Now, if it's a strong electrolyte, such as sodium chloride, NaCl, if I use my solubility chart, we would find that it is completely soluble. In terms of solubility, what Ksp has to do with is those slightly soluble salts. So if we're looking at a solubility table, the insoluble salts, if we can convince just a small amount to dissolve into the water, so it's allowing us to calculate in moles per liter how much of a salt can dissolve in water. All dissolving is a process of equilibrium, dynamic equilibrium. So as sodium chloride is going into solution, dissociating to form its ions, there is a point where we reach something called saturation, that the volume of water is holding as much as it possibly can in that particular temperature and volume. And what we would begin to see as an equilibrium sets up, where the dissociation in the forward direction is exactly equal to the precipitation out of the solid salt. So aqueous ions in equilibrium with their solid is called a dynamic equilibrium. That's when our aqueous ions are in dynamic equilibrium with the solid salt. If there's not much solid, it will all dissolve. As more solid is added to the solution, it will become saturated. The term saturated means that particular volume of water is absolutely holding as much as it possibly can of that dissolved salt. And if I added any more, it would just simply sink to the bottom. Thinking about, for example, Kool-Aid and how horribly hard it is to get that last little bit to dissolve. It's creating a saturated solution. So the solid will precipitate as fast as you can get it to dissolve, and therefore we call it a dynamic equilibrium. The process of going into solution is indeed equal to the process of falling out of solution. So if we think about a general equation, if M positive stands for any metal cation, somebody's first name in an ionic salt, and the NM negative stands for whatever the non-metal anion is. So if we think of a metal with a subscript, little a, to a non-metal with a subscript, little b, and this is a solid salt, and this can also be an ionic compound. And this is when we have a metal and a non-metal. And again, we determine those subscripts from the charges, the ions. So if this was +1 and this was -1, it would be a 1-to-1 ratio. If this was a +2, it would be our metal and then our non-metal subscript 2. So here's what we get. We then have the number of metal A, that's the number of metal ions that would dissociate. We'll just put a positive charge there because we are assuming that it's a +1 charge, plus the subscript that was on the non-metal becomes its coefficient, and it will become the negative ion. And these are both, again, in an aqueous solution. So we have aqueous ions on the right and the solid ionic compound on the left. And as we begin to think about a process of dynamic equilibrium, an ionic salt dissociates to form its ions. The subscripts then become the coefficients on the product side. The process of dynamic equilibrium is simply a dissolving process of physical change. If we wanted to express this equilibrium in terms of an equilibrium constant, K, we have practiced for months now. Knowing our journey began with Kc for the concentrations, Kp for pressure, Ka for acids, Kb for bases, Kw for water. This one is now given a symbol of Ksp, the solubility product constant for a dissociation of an ionic compound in water. It's telling us the saturation point, solubility product. In my head, I always think saturation point, how much can actually dissolve in water? But the formula for equilibrium still remains the same, products over reactants. But recall, pure solids and pure liquids do not appear in an equilibrium expression. So we're simply looking at the metal ion raised to the power of its coefficient times the nonmetal ion raised to its power from the coefficient. There is nothing to set that over because the ionic solid does not appear in the equilibrium expression. Pure liquids and pure solids drop out. So we've developed the expression for any ionic compound as it dissolves in water. The Ksp is equal to the positive ion raised to its coefficient times the negative ion, the nonmetal, raised to its coefficient, which came from the subscript originally. The Ksp, this is called the solubility product for each compound. The solubility product for an ionic compound, as it dissociates in water, is simply the metal raised to its coefficient, the nonmetal raised to its coefficient, the solid drops out. It says, watch out, solubility is not the same as solubility product. Solubility product is an equilibrium constant, and we have become very confident to say equilibrium constants have no units. It will not change because it is a constant, except if I change the temperature. So generally you'll see KSPs reported out at 25 degrees Celsius. We understand that as the equilibrium position changes with the temperature. So equilibrium constants, there's no units. Solubility is an equilibrium position for how much can dissolve. In other words, it will have units, usually reported in grams of solute per 100 mils of water, or another common unit might be molarity, moles per liter of solution. So thinking about what might affect an equilibrium position. For example, from our first section in this unit, the common ion can change this. For instance, if I had in solution a positive ion that was in common with the metal, we know according to Le Chatelier's, it will shift left, pulling some out of solution. I can change the amount in solution that's dissolved by adding a common ion, and we practiced that in our first section. The constant remains the same, but the solubility could change if I change things like having a common ion, or if I dissolved it into an acid, for instance, or into pure water. Things that can manipulate the amount of concentration, that's the solubility part. The constant is always the same. So let's look at an example to help us make sense, calculating Ksp from solubility. So we have here solid silver chromate is added to pure water. So first I'm going to just make sense of this silver chromate. We know silver is Ag, and it's a +1, and chromate is CrO4 with a -2 charge. So just to write this compound is Ag2CrO4. And it says some of the solid remains undissolved at the bottom of the flask. The mixture is stirred for several days to ensure that equilibrium is achieved between the undissolved silver chromate and the solution. So this is telling me that we have a saturated solution. That means that all of that has been mixed up and dissolved, but there's still some solid that's remaining after days of trying to get it to dissolve. So that water solution cannot hold any more ions. So this is formed in equilibrium, and it is formed 2 Ag plus ions, right? Because we have 2 over here, and 1 Cr, and this is an aqueous solution. and a CrO4, 2 minus, and just one of those, also an aqueous solution. It says that analysis of the equilibrated solution shows that its silver ion concentration is 1.3 times 10 to the negative 4. Here's my silver ion, 1.3 times 10 to the negative 4th molarity. Assuming that silver chromate completely dissociates in water and that there are no other important equilibria involved, meaning there's no common ion effects and whatnot, nothing else involving those ions. Calculate the Ksp for the compound. Now, we know that Ksp is equal to our products over reactants, and we have our Ag, so we're going to take our Ag plus, and since there is a 2 in front of it, we're going to square that, times our CrO4, 2 minus, and there's only 1 there. And remember, this would be over my products, but this is solid, and solids drop out. Now, I do know my silver concentration, but thanks to stoichiometry, we can find this chromate because there's a 2-to-1 ratio. So all I need to do is take my silver ion concentration and cut it in half. 1.3 times 10 to the negative 4th divided by 2. 6.5 times 10 to the negative 5th. And again, I know that because I can say, take this molarity and then say, well, there's 2 moles of silver for 1 mole of my chromate. So I just took this divided by 2. So now I just need to plug it in, and I need to take my silver, my 1.3 times 10 to the negative 4th m. We're going to square that, and then times that by 6.5 times 10 to the negative 5th. That'll equal my Ksp. So let's do this. Our 6.5 times 10 to the negative 5th, and we're going to times it by 1.3 times 10 to the negative 4th squared. And we get 1.098, so 1.1 times 10 to the negative 12. Let's look at the next example on the back of the page. We have a saturated solution of magnesium hydroxide. Let's write down magnesium hydroxide. Mg is 2 plus, and hydroxide is minus 1, so MgOH2. It's in saturated solution in contact with undissolved solid is prepared. All right, so let's see this dynamic equilibrium that we're creating. We have Mg2 plus in aqueous solution, and then we have 2 hydroxides. The pH of the solution is found to be 10.17. And we know that pH if we were to do 10 to the negative pH, we would get our H plus. So let's find if we can find POH. If we do 14 minus 10.17, that'll give us our POH. 14 minus 10.17. So our POH is 3.83. So now we can do 10 to the negative 3.83 to get our concentration of hydroxide. So 10 to the negative 3.83, 1.48 times 10 to the negative 4th. And so that's our concentration of our hydroxide. Now we can find the concentration of our magnesium. Again, this is in molarity because I know that this magnesium is half of my hydroxide. It's a 2-to-1 ratio. And we could show that by, if I said 1.48 times 10 to the negative 4th molarity of hydroxide we could say, well, there's 2 hydroxides for every 1 magnesium. So it takes this number times 1 divided by 2. So we're just going to divide this by 2 to get 7.395, so 7.4 times 10 to the negative 5th. Okay, now let's set up our Ksp. I'm going to go over here to the left. Our Ksp is equal to our magnesium concentration times our hydroxide ion concentration squared. So that is equal to 7.4 times 10 to the negative 5th times 1.48 times 10 to the negative 4th squared. Let's see what we get here. 7.4 times 10 to the negative 5th times 1.48 times 10 to the negative 4th. And we're going to square that. Go back here, put this in parentheses. We should get 1.62 times 10 to the negative 12th for our Ksp. 1.62. Again, there's no units for that. Molarity cancels out. Let's look at this next one. This time we're given a Ksp for calcium fluoride. It's 3.9 times 10 to the negative 11th. So first thing I'm going to write down is my calcium fluoride. I've got Ca is 2 plus, F we know is minus 1, so it's going to be CaF2. And assuming that calcium fluoride dissociates completely, so we're forming a dynamic equilibrium with calcium 2 plus ions and fluoride 2 fluoride minus 1 ions. These are my dissociated in aqueous solution. This is my solid salt. Now we are also told that our Ksp is 3.9 times 10 to the negative 11th. That's also telling us that we know Ksp is equal to our concentration of our Ca2 plus and our F minus squared. That's also, if I were to go take it one step further, we know that our Ksp, we could plug in right here, 3.9 times 10 to the negative 11th is equal to, now, I don't know what the concentration of my calcium 2 plus is, but what if I said our calcium 2 plus is going to be equal to X, and my fluoride is going to be equal to 2X. So let's plug that in down here. We can say this is equal to X times 2X squared. Now let's simplify this even more. We're going to say our 3.9 times 10 to the negative 11th is equal to, this would be 2 squared is 4, x squared times x would be 4x cubed. All right, let's do some even more simplifying. We'll bring it up over here. I'm going to take my 3.9 times 10 to the negative 11th. 3.9 times 10 to the negative 11th. Divide it by 4. And then in order to get rid of a cube, I have to take it to the power of 1/3. And I should get x is equal to 2.136. So x is equal to 2.136 times 10 to the negative 4th. And we know that this x is telling us that that's our concentration of the calcium ion. We also know that this is a 1-to-1 ratio with our calcium fluoride. So I can say that that is equal to our x which is also equal to the concentration of CaF2. So now we're going to write this as 2.136 times 10 to the negative fourth moles per liter. That's what molarity stands for, is moles per liter of CaF2. What do we want? We want, this problem wants calcium fluoride in grams per liter. Right now we have moles per liter. So we just need the molar mass of CaF2. We're going to look at a periodic table. We got calcium is 40 and fluorine is 19, so plus 19. So we have a molar mass of 78. Again, I got to have down here my molar mass. 1 mole of CaF2 has a molar mass of 78 grams of CaF2. Moles and moles will cancel, and I'm left with grams per liter. So let's do that. 2.136 times 10 to the negative fourth times 78, and I get 0.017 grams per liter of CaF2. So let's go back and revisit what we did. We were told that we had calcium fluoride, CaF2, and I know that by looking at the charges, crisscrossing my charges. We have calcium fluoride dissociates completely, and there's no other common ions affecting its solubility. So we have Ca, and we have 2 Fs. We want to find grams per liter of calcium fluoride. Well, if it was moles per liter, that would be molarity. So we want to get there, and then we can go to grams per liter. We want it of our product. So we're given Ksp. We write our Ksp expression. We then plug in our given Ksp, and we set over on the right side, since we don't actually know either of these concentrations, we just say x and 2x. Then we say x, 2x, and of course we've got to square it. We simplify that, we get our Ksp is equal to 4x cubed, and we solve for x. Well, x is equal to our calcium ion concentration. If we really wanted to find fluoride, we could double it, but we know that we have a 1-to-1 ratio here. So my calcium is also equal to the calcium fluoride concentration, and that is moles per liter, and we just went on the grams per liter, so we multiply by the molar mass to get 0.017. And now let's look at our last problem in our notes. The Ksp for LaF3 is 2 times 10 to the negative 19. What is the solubility of LaF3 in water and moles per liter? Okay, so we want LaF3 moles per liter. That's our molarity. So let's write out what we know. The LaF3 is going to form an equilibrium to give us La3 plus and F minus, but remember I have 3 F minuses. So we're given our Ksp, 2 times 10 to the negative 19, and our Ksp is going to be equal to the concentration of La times the concentration of F minus 1 raised to the third power. So now we just need to plug in 2 times 10 to the negative 19 is equal to, and we don't know La and we don't know F, but we can say that La is equal to X. F is going to be triple the amount of our La, so we can say X times 3x cubed. We can't forget that cube. So now we're going to simplify even more. 2 times 10 to the negative 19 is equal to 3 cubed would be 27. 3 times 3 is 9. 9 times 3 is 27. 27x cubed times x is 27x to the fourth. So now let's do some simplifying to carve out x. So 2 times 10 to the negative 19 divided by 27 raised to the power of 1/4. Should get 9.28 times 10 to the negative 6, but double check me. 9.28 times 10 to the negative 6. Again, this is concentration, and this x is simplifying La 3 plus, but we know that that's also equal to, it's a 1-to-1 ratio to LaF3 concentration. And that just happens to be where our ending point is for this problem. We wanted moles per liter of LaF3. We got molarity, which is moles per liter of LaF3. So this is our answer. If it wanted us to go one step further, like the problem before, to grams per liter, remember molarity is moles per liter. So I would just need to multiply by the molar mass of LaF3. But we don't need to this time. And that concludes our notes for our KSP note pack.